All right, so continuing with rigid body equilibrium. Today we're going to go through a couple harder cases. So last video and last class, we dealt purely with two-dimensional equilibrium. Now we're going to deal with three-dimensional equilibrium. So last class, it was only not moving left and right, not moving up and down, and not rotating clockwise, counterclockwise. In 3 dimensions, I can move up, down, left, right, and also in and out of the page. So I'm going to need to have all my forces in the x direction be 0 to stop left and right movements, all my forces in the y direction be 0 to stop up and down movements, and all forces in the z direction to be 0 to stop in and out of the page movements. And then just like force is a vector, the moment's officially a vector as well. Again, in two-dimensional case, it was technically only the z component that I cared about, but now the moment could have all three components, an x component, a y component, and a z component, and these correspond to rotations around the three different axes. So things can either rotate around x, they could rotate around y, and or they could rotate around z, and those are three independent movements. So to stop those three independent movements, I need these three equations. So all my moments in the x direction add up to 0, stop that rotation about the x-axis. All my moments in the y direction equal 0, stop rotation around the y-axis. And all my moments in the z direction, like we saw in the two-dimensional case, stop the rotation around the z-axis. And so if I have all 6 of those equations now be satisfied, that is rigid body equilibrium in 3 dimensions. And so just like the two-dimensional case, my point that I take the moment around can be any point I want. So I can take point O to be wherever I want. I can also take it to be different points. So if I want a different point around the x-axis than around the y-axis, that's fine too. So I can also change up my different points. I can also actually have more moment equations if I want. So just like we saw for the two-dimensional case, I didn't necessarily need to do 2 forces in 1 moment. I could have done 3 moments. I can actually have 4 or 5 or 6 moments here if I want to as well. But again, need to be careful that those points don't lie all along the same line. And here there's also conditions of if I'm in the z direction, they can't both be on that same z direction. And so there's some rules about where points can be when you do different points for the different moments. So you have to be careful with that as well. 6 equations in 3 dimensions instead of 3. So that means we can solve for up to 6 unknowns because I have 6 independent equations. Again, because I can write down more moment equations, might be tempting to write down 7 or 8 equations. But again, if you do that, they'll end up being linearly dependent on each other. So up to 6 unknowns for a 3D system, as opposed to the 3 unknowns we saw in the 2D system. So a bit more complicated, obviously, more equations and more unknowns, bigger systems, also kind of more complicated geometry with the different moments involved. So first thing we always do is draw the free body diagram. And just like we did in 2D, when we draw the free body diagram, we need to replace the support conditions with their appropriate reaction forces and or moments. So 3D system has a few different terminologies for the support conditions. So this thing could either be sitting on a ball or on a frictionless surface. So a frictionless surface is not going to stop any horizontal movements. Same thing for the ball. It's kind of like a roller. It can roll around, not going to stop any motion in the probably X or Y directions is how it's done here. But the floor will stop it from moving up and down. So the floor stopping it gives it that one reaction force in the vertical direction, just like we saw before. Same thing for the cable. Whichever direction that cable's going in, there's a reaction force in that same direction. And of course, cables only pull on things. You can have short links in 3 dimensions as well. Again, very similar to the cable, just along whatever direction it's going in. But the short link can pull or push, so either in or out, depending on which way it's going. Next up are rollers. So if I actually have a roller either on a rough surface or a roller on a rail, the rough surface is going to stop any sort of motion perpendicular to the direction of this wheel, or this rail will stop any motion perpendicular to the direction of the wheel, but this thing can roll back and forth in the left and right direction the way this is drawn. So no force in the left and right direction, but there is a force coming out of the page. So in the z direction as drawn here, and then there's also a force in the y direction because that's going to stop it from moving through the floor. So it's kind of a normal force in the y direction, apparently. That's what they call it. If I have a rough surface, friction is going to stop this thing from sliding horizontally, so both in the x and y directions. The floor is going to stop it from moving up and down. So 3 forces in that case, x, y, and z. Ball and socket joint is kind of the 3-dimensional equivalent of a pin. So a pin stops motion in the x and y directions, but does not stop rotation. Same thing for ball and socket joint. It's kind of stuck there. It's not going to move left to right, up, down, in, out of the page, but it can rotate around. So no prevention of any rotational motion, just prevention of lateral motions. So it just forces x, y, and z directions. Then fixed support. So again, if I stick this thing into the ground or stick this thing into the wall, that's going to stop it from moving left and right, going to stop it from moving up and down, going to stop it from moving in and out of the page. It's also going to stop rotations no matter what direction I put it in. So it doesn't matter where I push it to left, in and out of the page, up and down. It's going to stop all sorts of rotations. So 6 total reactions there, 3 forces and 3 moments in all 3 directions for any sort of fixed support anytime something's stuck into the ground, stuck into the wall, or welded to it, whatever the case may be. Then a couple other specific 3-dimensional objects, a universal joint. I'm going to stop it moving left, right, up, down, so all 3 forces. It's also going to prevent rotation in one direction and one direction only, and that's this horizontal left-right direction here. I believe that's called X, some moments around the X-axis. And then another thing we see sometimes are bearings. So bearings, basically I have this pole slotted through a hole. And so if it's slotted through this hole, this guy is assumed to be frictionless. So if it's frictionless, this pole can slide in and out. So because it can slide in and out, there's no force in that in and out direction. But there is a force perpendicular to it in both directions because it's not going to come out of that hole. So force in the what they call y and z directions, basically stopping it from coming out of the hole, but there is no resistance to motion along the axis of the pole going through the hole, so no force in that third direction. It's also going to stop it from rotating around the y-axis, so it can't spin around like that. It can't spin around around the z-axis. It can't spin around like that, but it can spin around its own axis, so you can twist this thing around through the hole. So no moment in that third direction. So 2 moments and 2 forces for that guy. And then there's also the hinge or the bearing with kind of little blocks here. So these little blocks are actually stopping it from sliding through that hole. So that adds the additional force in that third direction, stopping it from sliding through that hole. You can still twist it, so it can still be spun around through the hole, but it can't slide back and forth. Same thing for things like hinges, same sort of thing there. They don't move left, right, don't move up, down, don't move in and out of the page, and they only rotate around one certain axis. And so that one certain axis is the only reaction force or moment we don't have. In terms of the overall procedure, again, very similar to, actually exactly the same as the 2-dimensional case. First thing you want to do is draw your free body diagram, have your coordinate system established, take away any support conditions, any walls, cables, ball sockets, whatever you have, and replace those with the appropriate forces and or moments for those supports. Label all the forces and moments acting on it externally, and reaction, any sort of dimensions also might be relevant as well. Then once I have that, I can write down my equations of equilibrium. So in this case, I have up to 6 of those. To solve for those, again, generally our unknowns here are those reaction forces, so tension in the cable or normal force, whatever I'm trying to solve for. And again here, most cases, easiest thing to start with is a moment equation, because your moment equation, if you do it around the right axis, around the right point, you can probably end up with an equation with only one unknown. And then once you have that unknown, you can go and move to either a force equation or another moment equation around a different axis or around a different point, and you can solve for another unknown. and kind of keep going until you have all of them, whether it's 3, 4, 5, or 6, whatever many the problem has. So again, that's generally the way you should go about doing this instead of trying to write down a 6x6 system of equations and having a fancy calculator do it. Try to do it the clever way where you can find one moment equation around a certain axis, around a certain point that gives you only one unknown, and kind of work your way through it that way. So that's a three-dimensional case. There's a few other two-dimensional cases that we didn't see last class. One of them was dealing with distributed loads. So every load we saw previously was just one single point load, concentrated load at a single location. And so to find the moment, it's just force times distance. And then that's how I did sum of moments. For distributed loads, easiest way to deal with those is actually convert them into a single concentrated load. So back when we did on day 8, take this distributed load, replace it with a single force at a single location. So day 8 tells you how to do that. And then at that point, you're basically reduced to the situation we had before, where everything is just a concentrated load, and I can add up all my moments, all my forces in that way. One thing to note about that is that works perfectly fine right now. So for now, that's the way to do things. Convert any distributed load into a concentrated load and then do things as normal. So finding external reaction forces works perfectly. When you get into internal forces, so we'll see a little bit of this at the end of the quarter in week 9. Also in your next class, CEE 220, Mechanics and Materials, you'll be dealing with a lot of internal forces. Inherently, distributed loads and concentrated loads are actually different, but we can put it into an equivalent load only for external force purposes. So anything external forces like we're doing now is perfectly fine. But later in this class and in other classes, you're going to want to keep those distributed loads as distributed loads to solve for internal things. The other situation we didn't run into yet is a single concentrated moment. So I can have actually, just like forces, I can have a bunch of forces acting on my object. I can also have individual moments acting at certain locations on my object as well. So instead of pushing down on this beam with a bunch of forces, I'm actually twisting this beam at a certain location with a certain magnitude of a moment in a certain direction, obviously. And so those will show up in both the examples during class today as well as in your homework. These are fairly easy to deal with. It's just another moment that shows up in your moment equation. So just like when you're taking all your forces, all my forces in the y direction, I'm just adding all my force in the y direction. When I'm taking my moments, you can take all your moments because each force creates a moment. So you'll have force times distance, force times distance, force times distance for all your moments like we did last class. But then if I have one of these individual moments, m0, I just add that in as well. So I have force times distance plus force times distance plus force times distance plus some moment plus force times distance, and just kind of all my moments from all my forces and moments go into my moment calculation. So moment around point A will have this m0 in it. Moment around B will have this m0 in it. Technically as a negative because technically he's going clockwise. So force times distance minus m0, blah, blah, blah. So fairly easy to deal with there. So during class today, we'll see some examples of three-dimensional cases, distributed loads, as well as concentrated moments. So I will see you then.